So you are looking at a paper today titled minWM, a full-stack open-source framework for real-time interactive video world models. This is from researchers at Shengshu, Tsinghua University, and several other institutions. If you're an ML engineer trying to build the next generation of generative engines, the absolute core insight you need right now is that this paper hands you an end-to-end, highly reproducible recipe.
Right. It's a completely open pipeline.
Exactly. A pipeline for converting those incredibly high quality, but, notoriously slow bidirectional text-to-video foundation models into camera-controllable, low-latency, autoregressive world models. And it does this through a strict two-phase process. Phase one is controllable fine-tuning, leveraging a method called PRO-PE for precise camera injection. And then phase two distills that model into a real-time generator using the causal forcing ++ pipeline, which is autoregressive diffusion training, causal consistency distillation, and asymmetric distribution matching distillation.
Yeah. And we really need to contextualize exactly why this is such a massive deal for the AI research community. I mean, if you look at the landscape of open weight video generation right now, we have models like WAN 2.1 and HY 1.5.
Phenomenal offline video generators.
Oh, absolutely phenomenal. You give them a text prompt, they churn for several minutes, and they hand you back a gorgeous, temporally coherent video. But they are completely static in their generation process. They lack the controllable, causal, low-latency rollout that you absolutely must have to build an interactive world model.
Right. You simply cannot build a playable simulation or like a dynamic game environment if your model requires you to generate the entire timeline at once bidirectionally.
Exactly. And this paper, minWM, bridges that exact gap. It takes the massive aesthetic priors of those foundation models, it engineers them into a streaming, interactive format.
So before you can make a model real-time, you first have to teach it how to move, right? It has to actually understand physical space, not just, hallucinate a pretty sequence of pixels. So let's look closely at phase one of the minWM pipeline, which tackles camera control. In video generation, forcing a model to respect strict 3D camera boundaries without destroying its image quality has always been this notoriously thorny issue. How are they mathematically enforcing this?
Well, the researchers solved this by adopting PRO-PE, which stands for cameras as relative positional encoding. To understand the mechanics here, we have to look at the math of how it injects the camera data into the architecture. Given a video clip, you have camera parameters for every single frame. You have the intrinsic matrix,
which dictates things like the camera's field of view and focal length, right?
Right, and the optical center.
Right.
Then you have the extrinsic matrix, which is your actual world-to-camera transformation in 3D space, where the camera is located and how it's rotated. PRO-PE lifts these intrinsic and extrinsic matrices and combines them into a 4x4 projective matrix.
Wait, so it's essentially just a 4x4 matrix that mathematically encapsulates the exact physical state and lens properties of the camera at any given microsecond.
Yes, but the real innovation is in how they apply it. For any given token in a frame, PRO-PE constructs a block diagonal transformation from that matrix. And then it injects this transformation directly into the self-attention mechanism using what's known as a GTA form, or gated token attention.
Let's pause on GTA for a second because, that's critical. A lot of engineers might just try to concatenate the camera coordinates as a raw input vector alongside the text embeddings and just hope the model figures it out.
Yeah, and concatenation often completely overwhelms the model's existing spatial priors. Gated token attention essentially introduces a learned gating parameter. It allows the model to dynamically decide how much the relative camera pose should modulate the standard attention score.
Oh, I see. So the attention interaction between any two tokens, say token A in frame 1 and token B in frame 5, explicitly depends on their relative projective transformation.
Exactly, but gated so it doesn't break the model. It jointly encodes the relative camera intrinsics and the camera poses, while protecting the base model's ability to just draw a realistic-looking scene.
Okay, to give you a mental image for this, imagine you have a standard attention mechanism. Usually it's just looking at a flat grid of latent pixels, trying to figure out which pixels are important to each other based on the semantic text prompt.
Right, a purely semantic understanding.
But PRO-PE essentially gives that attention mechanism a pair of high-end VR tracking sensors. Instead of just knowing where a pixel is on a 2D screen, the model now explicitly understands the relative 3D spatial relationship, the exact physical camera pose between any two tokens across time. And because of that gated token attention, it preserves the original generative structure. It doesn't overwrite the brain of the model, it just gracefully hands it a new spatial awareness.
That's a highly accurate way to visualize the mechanism. It preserves the generative prior while strictly enforcing geometric constraints. But here is where we hit a fascinating bottleneck. And this is a crucial insight from the ablation studies. The researchers obviously needed a massive amount of data to train this phase 1 camera-controllable model.
Data is always the bottleneck.
Always. So initially, they tried training it with a data set called spatial vid. Now, spatial vid uses perception-estimated camera poses. This means they took existing standard 2D videos and ran them through perception software to estimate or, guess the camera trajectories.
Which is standard practice in a lot of computer vision pipelines when you lack ground truth data.
It is, but the training outright failed. The model simply could not learn reliable camera-controllable generation under this setup.
Okay, wait, I have to push back on this, or at least raise a critical question that you are probably thinking right now as an ML engineer. Why is it that an advanced multi-billion parameter diffusion model, a model that can handle incredibly noisy, vague, poorly spelled text prompts and still generate an absolute masterpiece, why is that exact same architecture so incredibly fragile to slightly noisy estimated camera poses?
It's a fantastic question, and it fundamentally comes down to the difference between semantic manifolds and geometric manifolds. When a model processes a text prompt, the semantic space is very forgiving. It's continuous.
Right, futuristic car versus sci-fi vehicle.
Exactly. The latent representation is highly similar, so the gradients smoothly point toward the same conceptual neighborhood. But geometry is absolute. The 3D projection matrix relies on strict, unforgiving mathematical consistency.
Because it's literally mapping 3D coordinates to a 2D plane.
Precisely. If your estimated camera pose is slightly off from frame to frame, which perception software often is, the relative projective transformation you are feeding into the attention mechanism actively contradicts the actual pixel movement in the visual data. You are essentially gaslighting the self-attention layers.
Oh, wow. You are mathematically telling the model the camera moved exactly 2 inches to the left, but the physical pixels in the training video moved 3 inches.
Yes. So the gradient updates become chaotic because the model is trying to reconcile an impossible physical reality. It fails to converge on a controllable representation because the underlying rule you're trying to teach it is constantly shifting.
So you have a multi-billion parameter model basically having an existential crisis because the math and the visuals don't align. How did they bypass this data bottleneck? Because they clearly got it to work for the final open source release.
They bypassed it by entirely abandoning estimated poses and relying strictly on effectively ground truth trajectories. They used 2 primary strategies to curate flawless geometric data. First, 3D reconstruction and re-rendering. They took physical scenes from the DL3DV dataset, used advanced techniques to completely reconstruct those 3D environments, and then rendered perfect, mathematically exact videos along prescribed camera trajectories.
So they basically treated reality like a game engine to extract the exact math.
Yes, exactly. And second, for the broader open source version, they used synthetic generation. They took images from the OpenVid dataset and pushed them through existing, already trained world models like WorldPlay to generate videos with absolute known camera movements. By providing clean, flawless geometric data where the matrix perfectly matched the pixel movement, the gradient variance stabilized, and the model successfully learned camera controllability.
That is a masterclass in data curation right there. Garbage in, garbage out, especially when it comes to geometric math. So, we've solved the spatial problem. The model knows exactly where the camera is and respects its boundaries. But if you try to plug this phase 1 model into a video game engine right now, it crashes.
Oh, definitely.
Because it's highly, highly slow, and it's trying to render the end of the timeline before the beginning. It is bidirectional, meaning it needs to see the future to generate the past, and it takes multiple denoising steps. We have to force it to only look at the past, and we have to make it stream.
Exactly. We need to convert this into a fast, autoregressive student. This transition is phase 2, the causal forcing ++ pipeline, and is broken down into 3 stages. Stage 1 is autoregressive, or AR, diffusion training. They take the camera-controllable multi-step model we just built, and they shift the training objective to AR chunks. Specifically, they use a chunk size of 4 latent frames.
Just 4 latent frames at a time, that feels, incredibly small for a model that's used to processing entire video sequences.
It is small, but that's by design for latency, and they enforce strict causality. The model is forced to predict the clean frame conditions strictly on historical prefixes. It is no longer allowed to look ahead in time.
That's a massive paradigm shift for the architecture. It teaches the model to generate the future purely from the past, which is the foundational requirement of any interactive streaming system. But even after this step, it's still fundamentally a standard diffusion model, meaning it still requires too many denoising steps to get a clean image.
Right. If you have to run 50 diffusion steps for every 4-frame chunk, you're still measuring your frame rate in seconds per frame, not frames per second. How do we compress the steps? That is stage 2, causal consistency distillation, or causal CD. Now, the paper notes that they could theoretically use causal ODE initialization here, but they specifically highlight causal CD as the breakthrough.
I want to dig into this because this is exactly the kind of deep technical point that ML engineers need to pay attention to. Why the hard distinction between causal ODE and causal CD? What is the actual mechanism saving us here?
To understand the mechanism, you have to look at what causal ODE initialization actually requires. It involves generating offline ODE data probability flow, ordinary differential equation trajectories, to teach the student model how to take larger steps through the noise space.
Right.
Generating this data offline is an absolute nightmare of time and storage. You are talking about saving massive multi-gigabyte tensors for every single time step of every single video in your dataset.
Just to act as the ground truth for the student, so you're basically caching the entire slow generation process to a hard drive so the fast model can read it and mimic it. I can see the AWS bills skyrocketing just thinking about that storage overhead.
Precisely. It's unmanageable. Causal CD is theoretically equivalent in outcome, but it mathematically bypasses the offline data curation entirely. Instead of comparing the student to a pre-computed trajectory on a hard drive, causal CD enforces consistency across the trajectory directly during training.
So it minimizes the distance between the student's prediction at the current step and the student's own prediction at the previous step, guided by the teacher's structure.
Yes. It forces the model's own outputs to be self-consistent along the trajectory. It's an elegant mathematical shortcut that eliminates the massive storage and compute overhead of ODE trajectories.
I absolutely love when advanced math actually saves us money on infrastructure. So we now have a fast, autoregressive model that doesn't need 50 steps. But as the researchers point out, the quality of this few-step AR model is, well, it's a bit degraded compared to the massive offline teacher we started with in phase 1. It's fast, but it's gotten a little sloppy visually. The lighting might be off, or the textures might blur during fast camera movements.
Yeah, the generative quality is constrained by the AR limitation. It inherits the imperfections of predicting strictly from the past with very few steps. It loses that holistic view of the scene.
Which is exactly why we need stage 3, asymmetric DMD, or distribution matching distillation. Now, you often hear distillation explained with the cliche of a fast but clumsy student and a slow but brilliant teacher. That tells you what is happening, but it doesn't explain how the math actually pulls the distribution. Let's use a more mechanical metaphor here. Think of the few-step AR student model like a race car driver navigating a highly complex track in thick fog.
Okay, I like where this is going.
The driver is incredibly fast, but they are guessing the exact curvature of the turns based on limited memory of the past. That's your autoregressive rollout. The teacher model, the frozen bidirectional model from phase 1, is like a drone hovering directly overhead with a perfectly clear view of the entire track.
Right, the drone sees the true optimal physical curve.
Exactly. So what is the asymmetric gradient doing? The asymmetric gradient is essentially a real-time radio signal yanking the steering wheel back when the driver starts drifting off the true physical curve of the track. It doesn't force the drone to drive the car, it just applies a corrective force to the driver's current trajectory. How does the math of asymmetric DMD actually execute that steering correction?
Technically, this relies on calculating the KL divergence, the Kullback-Leibler divergence, using standard DMD gradients. What they are doing is calculating the score of the generated sequence, the blind rollout from our race car driver. They use a frozen real score model, that's the drone overhead, the high-quality bidirectional teacher, to estimate the score of that sequence in the true, flawless data distribution.
And simultaneously, they use an online trained fake score model to estimate the score in the student's current slightly flawed distribution.
Right. And by minimizing the KL divergence between these two distributions, the asymmetric DMD gradient forces the fast student to output frames that look exactly like what the slow teacher would have produced. It calculates the difference between the two scores and uses that difference as the loss to update the student.
And crucially, all of this, the real score, fake score, and the student, are conditioned on the strict camera trajectories we established back in phase one. The geometry remains locked in. So, we've walked through the underlying mechanics. P-bro PE and gated token attention for control, the strict need for ground truth data to avoid gaslighting the gradients, AR chunks for causality, causal CD to save our hard drives, and asymmetric DMD to yank the steering wheel and fix the visual quality. Let's pivot from the theoretical math to what is arguably the absolute goldmine of this paper.
The engineering pragmatics.
Exactly, the reproducible engineering pragmatics. This isn't just theory. They actually built this, and they've given the ML engineer listening the exact recipes to do it themselves.
Yes, minWM is designed as a modular and architecture extensible paradigm. They tested this pipeline on two major open backbones to prove it works across different underlying architectures. The first is WAN 2.1, which is a 1.3 billion parameter model. The second is HY 1.5, which is a much larger 8 billion parameter model.
So they cover both cross-attention-based condition injection and MDIT-style architectures.
Right. And for both backbones, the final distilled world models are generating four 80 by 832 resolution videos at 77 frames, executing just 4-step distillation inference. That is remarkably fast for that resolution.
4 steps to a clean frame. I mean, that is the dream for real-time interaction.
Yeah.
Getting there requires hitting the exact right hyperparameter lottery, which brings us to the batch size ablation. I want to slow down here because this is where training runs either succeed or burn thousands of dollars in compute for nothing. They broke down the specific batch size findings for the 1.3 billion parameter WAN 2.1 model, and the results are incredibly stark.
Very stark. If you try to train this with a batch size smaller than 4, it is an outright failure. The model completely fails to learn camera controllability.
And if you bump the batch size up to 8,
the controllability improves substantially, but it remains highly unstable during training. You get these wild, volatile fluctuations in the loss curve. It isn't until you hit a batch size of 16 that you find the magic number for that specific model size. At batch size 16, you finally get stable, high controllability training that successfully completes the pipeline.
Okay, let's unpack the why here. Why is geometric conditioning so hypersensitive to batch size? Why does 8 fail wildly where 16 succeeds? I imagine it has to do with the gradient variance we talked about earlier with the spatial data.
It absolutely does. When you are updating the attention weights to map a 4x4 projective matrix to a visual output, the target is extremely rigid. Think about what is happening in a small batch of 4 videos. Video 1 might feature a fast pan left. Video 2 might be a slow, creeping zoom. Video 3 is static, and video 4 is a complex diagonal translation.
So you have 4 wildly different geometric vectors all trying to pull the weights in completely different directions simultaneously.
Exactly. In a small batch, the gradients representing those geometric transformations are too noisy. They are fighting each other. The average gradient step doesn't provide a stable enough signal to cleanly update the self-attention mechanism. Instead, it causes catastrophic forgetting of the model's foundational visual priors because the attention layers are being violently yanked in contradictory directions.
You need a sufficiently large batch 16 in this case to smooth out that gradient variance.
Right. A larger batch provides a consistent, unified directional update to the weights that reveals the true underlying mathematical rule of camera movement, rather than just confusing the model with a few loud exceptions.
That makes perfect sense. You need enough diverse geometric examples in a single backprop step to prove the rule to the model. So for the engineers looking to replicate this on the massive 8 billion parameter HY 1.5 model, let's go over the exact step-by-step training recipe they use because the scale changes things.
For HY 1.5, because of that massive parameter count, they use a batch size of 32 to guarantee stability. They use a learning rate of 1e-5. First, they train the phase 1 bidirectional model for 8,000 steps to lock in the camera control. Then they move to the phase 2 causal forcing plus pipeline.
Okay, so breaking down phase 2.
Right. They do 4,000 steps of the stage 1 autoregressive training. They follow that with 1,500 steps of the causal CD initialization. And finally, they finish with just 500 steps of the asymmetric DMD.
That contrast is fascinating. 8,000 steps to teach the model spatial awareness, but only 500 steps of asymmetric DMD to lock in the final visual quality. It really highlights how fundamentally difficult it is to rewire the attention map's geometry compared to just applying a quick visual polish on an already spatially aware autoregressive rollout. 500 steps proves how ruthlessly efficient that asymmetric gradient is once the student is in the right neighborhood.
Absolutely. And we also need to touch on the inference side of the engineering pragmatics. The framework supports streaming DIT denoising and streaming VAE decoding.
Let's quickly define those for anyone unfamiliar with how they operate in a streaming context. Streaming DIT diffusion transformer means you are processing the latents patch by patch temporally rather than waiting for the entire sequence's tokens to be computed at once. You are cascading the computations.
Right. And streaming VAE decoding means that as those latent chunks arrive from the DIT, the variational autoencoder turns them into actual RGB pixels on the fly. You don't have to wait for the whole video chunk to finish denoising before you start rendering pixels to the screen. It creates a true real-time loop that mimics how a game engine actually pushes frames to a display.
This is why minWM is so valuable. They aren't just dropping a static finished checkpoint on Hugging Face and saying, here's a cool model, good luck figuring out how we built it. They are handing over the entire architecture extensible paradigm.
And by open sourcing the intermediate checkpoints for every single training stage we just discussed, they are allowing researchers to jump in at any point. If you want to use their highly stable, controllable phase 1 model, but you have an idea for your own custom phase 2 distillation algorithm, you can just download the 8K step checkpoint and start experimenting from there.
Or if you want to adapt an existing world model to a new proprietary data distribution or a different latency target for your specific application, the minWM framework supports that adaptation completely out of the box. It fundamentally lowers the barrier to entry for building interactive world models. You don't need to invent the causal pipeline from scratch. The scaffolding is entirely built and documented for you. But as we wrap up this analysis for today's AI paper slop, I want to leave you with a final thought to chew on. We just spent a lot of time analyzing Phase 2, Stage 3, that asymmetric DMD masterclass where the drone overhead, the frozen, brilliant bidirectional teacher calculates the exact KL divergence to correct the fast autoregressive student. Right now, with 1.3 or 8 billion parameter models, that works beautifully. But as our underlying foundation models inevitably scale to 100 billion or even a trillion parameters, that teacher model is going to become unfathomably massive. It will inherently understand complex light transport, fluid dynamics, and microphysics flawlessly. So will the absolute bottleneck for creating real-time physics simulators and next-generation game engines simply become the raw compute cost of running that massive teacher's critique during the distillation phase. If we can perfectly distill the physical reality of a trillion parameter model into a 4-step generation process running at 60 frames per second on consumer hardware, how long until traditional hard-coded game engines like Unreal or Unity engines that rely on explicit polygon math and simulated ray tracing are entirely replaced by streaming neural representations generated on the fly?